but please do ask any questions. And because I'm probably going to talk very fast, if I do talk too fast, please ask me to slow down. Fabulous. So I'm going to give a little bit of an overview, and then I'm going to look at some of the applications that D-Wave has been working on up till now. Really quite surprising, because if I was giving this talk about 2 years ago, then I would talk about the idea that we're primarily looking at optimization problems, and we've been running about 2 or 3 problems to get completed. Right now, as you'll see from the slides, we're probably looking at about 100 real applications that we've been working on in different organizations, and I'm going to run through a few of those. So D-Wave was founded in 1999. We have 4 machines and applications for 4 various countries and companies. Lockheed Martin was the first company, followed by Google. Los Alamos bought their machine a couple of years ago, and we have one machine somewhere in America, but we probably wouldn't guess where that is. And Oak Ridge National Laboratories, very quite similar to Tilda. They offer supercomputing facilities for the Department of Energy in America, and they are building room for their exoskeleton machine. Within that, they reserve space which may be used to have 2 people in who will effectively act as accelerators that might be requirements with the exoskeleton. So whilst they're waiting for that building to be completed, they're actually they have their machines are using Coupa, and they're using we have about more than 30 other customers using the remote access method to access the D-Wave supercomputer and quantum computer and run their applications on the computer. These are the 30 paying customers, and obviously there are then probably about 1,000 of you who are using it because they've demonstrated to us. Somebody wants to deal with can everybody hear me from here? Oh, I'm sorry. Oh, yes. Okay. No, that's fine. I move around a lot. Okay, I'll try and stand still for the duration. So yes, we have many other users. Often universities will come to us and say, we're looking at this fantastic application. Could we have some machine time? And if I'm feeling very generous, then I say, yes, you can have a few minutes on the quantum machine. Okay, so how does this thing work? So you're probably all very familiar with classical computers that have transistors that create gates, and hence we have the gate model for quantum computing. Well, the D-Wave quantum computer is completely different to that. So we use a technique called quantum annealing, and effectively we program all of our qubits. We currently have 2,000 qubits, and we program them to create effectively an energy landscape that might look something like this in a 3D environment. So if this was the Alps, then we would create, by programming the weights and the coupling strengths between the qubits, we would create this landscape. We would then run our quantum machine instruction, which is the algorithm we're trying to generate and create. And after a certain amount of time, the quantum computer will respond with the answer to that problem, which will probably be the lowest valley, if you think about it like this, or the lowest energy state of this energy landscape. Okay? That's about all I'm going to say on that. So if anybody wants to talk to me later, I'll be around all day. So obviously we have a lot of different customers and companies that we're working with in Europe, and I'll go into some of their applications. And I'm often asked the idea of what would a quantum computer center look like? And we kind of we have it as sort of like it's an imaginary type of idea at the moment. However, at D-Wave, we don't have to dream about these things, because we actually have a quantum computer data center based in Vancouver, or Burnaby, our headquarters, And here is a picture of two of them. These two are used for the remote access. They sit and hum away all day like this. And in the other parts of this room, then there are another 16 D-Wave machines in different stages. Some are being researched, some are being developed, and some are acting as standby. So again, if we open one of the doors of those big black boxes, we would see inside a dilution refrigerator, very similar to a lot of other people who are doing quantum computing research, and effectively this is all we would see. The size of the device is such that the outside walls actually create an electromagnetic shield, a Faraday cage, and so we have the size of it so people can actually be operating inside while it's working without having any electromagnetic interference. If we were to remove all of those cans, those shieldings in the dilution refrigerator, this is what we would see inside. So this bar at the very top of the system is at room temperature. We then drop to, with using liquid nitrogen, to 77 degrees Kelvin, and then by using various isotopes of helium, drop all the way to 15 millikelvin. And at the moment we're actually running at 12 millikelvin, and part of our development is to reduce that temperature because all temperature is noise from quantum computing environment. The lower temperature we can get closer to the theoretical zero that we're trying to achieve, which would give us a perfect error-free state. One thing to note here is the fact that unlike classical computers, then the whole of the device, that includes the quantum processor, the servers in and out of the machine, and all of the pumps in the dilution refrigerator, they only consume about 5 kilowatts. This is what one looks like. I actually have a wafer here with a variety of the 2,000 qubit chips on it, which we are testing, and then we cut up and put into the machine. So if anybody wants to have a look at those, they're quite welcome to. This is actually the chip itself, and if you I can see them down here. Am I not speaking loud enough, or is this microphone not working? Okay, I'll stay here. I don't mind. Okay, maybe everybody can hear me better from a streaming point of view. Okay, so with anybody with any keen eyes, we can see that there is a grid here made up of a variety of different unit squares. Each unit square contains 8 qubits, and we have 16 by 16, giving us 2,048 qubits. When we actually calibrate the machine, we know we're going to lose a couple of qubits, which we can't calibrate to be identical to all of the others, and so that's why we say that we have 2,000 rather than the 2,048. Once we've managed to get 2,048, but that was a rare event, and typically they have about between 2,030 and 2,040. Okay, so we started out with 4 16 qubits, like most of the gate model machines today, and we've managed over the time to double the number of qubits every 2 years or so. So kind of like very much a Moore's law for quantum computing. And when we bring out our 5,000 qubit system in 2020, then that will have more than 5,000 qubits, and that will keep us on this same trajectory. Okay, so that's about all there is about the hardware. So if anybody wants to talk to me about that later, then I'm quite welcome to discuss that. From a application point of view, then it was one thing that's quite interesting is the idea that when people think about the D-Wave quantum annealer, then they turn around and say, yes, but you've got a very limited amount of application space and problems that you can solve. And originally, then we probably looked at everything that was optimization. But since then, and some of the examples will show you, we've actually done a variety of applications in machine learning and artificial intelligence, as well as material science, and these others are sort of things that don't fit in those categories, as you'll see when we get going. So these slides now are the slides that the customers involved have produced themselves. So I haven't created these; they are their slides. So it gives some sort of some proof to the idea of what they're trying to do. It's not been made up by D-Wave. So Volkswagen, they basically about 2 years ago, they said, "Hey, we'd like to do some investigation, some research in quantum computing, and what sort of things can we do? Is there something that we can do within the motor industry that might have a bearing on quantum computing?" And so we actually put together a list of 10 different ideas that might be useful for Volkswagen, and traffic routing was probably idea number 9 or 10. But all of the others were things that the VW could not really talk about. Nobody in the street wants to talk about developing batteries for electric cars. So we chose traffic routing on the basis that it would be an application that you could tell your grandmother about and she would understand. And that was quite important to VW, because if you can imagine, 2 years ago, then the Dieselgate scandal was going on, and they wanted to have a bit of a diversion, and they thought that quantum computing would be a good idea. So effectively, they had data from about 10,000 cars in Beijing, and you can see that the actual sort of heat map of where those taxis were is quite congested where the red areas are. So they were saying, fine, let's try and reroute those taxis to reduce the congestion within Beijing. Big problem, though, is the fact that 10,000 taxis doesn't fit onto a D-Wave chip, onto the 2,000 qubits. So they said, okay, so what if we choose an area, and in fact, from the Beijing airport to downtown Beijing, there are about 430 taxis. So we said, well, that's still a bit too big, and you can see where we're going with this. However, we do have this bit of software called QBSolve that allows us to decompose a problem, and we could probably do about 430. So let's have a go and see what happens. So this was the original congestion between the airport up here and downtown, and we were able to actually reroute the taxis going on a variety of different paths so that the congestion was reduced. So they were very pleased with that. We made a lot of headlines, and they've now gone on to do other applications that you'll see in a minute. Now, there is then a company in North America called Booz Allen Hamilton. They're a defense engineering company, and they said, yeah, okay, so it's all very well rerouting all these taxis, but wouldn't it be better if we could do something better than that? So they said, well, how about rerouting satellites and see whether we can optimize the satellite journeys so we can do better targeting for photographs or other military operations. And having succeeded in doing that, they then said, well, okay, we could do all of these type things as well. So isn't that great? And they concluded that yes, they can investigate small problems today, and that's very much a theme of what we're doing at the moment. And in the future, they can look, when we have bigger machines, better software, better decomposition mechanisms, we can actually provide much better resources for doing some of the work that they're doing. This is, you can't quite see it down here, but this is the DLR symbol for the German space agency, a bit like NASA. And they said, yeah, well, okay, what about car routing? That's not particularly interesting for us. Satellites, yeah, we do some satellite stuff. But how about something real world, like rerouting aircraft across the Atlantic? So they took this problem and looked at it, and as you can see here, they were able to route a certain number, a small subset of all the traffic across the Atlantic, and they basically proved to themselves and other people that this was a possibility for quantum computing. The Denso, I don't know whether you're familiar with Denso. They used to be part of Toyota. They actually have been split out now, and they do a lot of the parts for Toyota cars. And they basically said, well, if we were to take what they called the VW Bible of doing the traffic routing, could we use that to do something a bit better? And there are hundreds of thousands of taxis in Thailand, and they thought, yes, we would try to do this. And they did the same sort of thing, reduced the model, and were able to do rerouting of some of those taxis. They've gone on, and you'll see the fact that Denso now, they're getting close to actually using an application, and I'll mention that in a minute. This is a very, very interesting one. Again, it's a Japanese company called Recruit, and they effectively do a lot of things, but a lot of internet advertising, web applications, and that sort of thing. And they basically said the fact that wouldn't it be great if we could actually optimize the advertisements that are put onto a smartphone by using the D-Wave machine. And so they constructed a model of taking the idea of what does somebody want, and there is an auction that goes on in terms of the minute you click onto a page, it's similar in your browser, an auction goes on in real time, and it's very, very fast, to determine who is going to display something for you as an individual. So Recruit did this, and they discovered that there was a 15% advantage from using the D-Wave system than in using classical computers. But there's one big problem. We can't use the D-Wave in real time today. There is too much of a delay between Japan and Vancouver, let alone the delay of getting the information down to the quantum computer. So we're obviously working with them to reduce those times so that in the future they can then be able to do this sort of internet auctioning remotely. So they said it's great. This is an application from BT in the UK, British Telecom, and we put a proposal together that was funded by the UK government to look at how could we reroute networking, avoid different targets from very important routers, big firewalls and those sort of things, to avoid hackers and incursions in the network. And they came to the conclusion again that that's what was going on. Am I running out of time? Oh, 2 minutes. Okay, really go fast. Okay, this is another interesting one. These guys took the VW cookbook again, or the Bible, and they're an online grocery shop. They have lots of different robots that are running around. They have to actually put an order together within 15 minutes of getting that order on the telephone. And so they basically work on rerouting those robots. And as you can see here, this is a development of what they did, and we had lots of collisions. They then did some more work and were able to take out of those collisions by developing the application further. So this here is another one in terms of if we look at various health options and we look at an individual, we can actually use a quantum computer to fill in the missing parts, if that makes sense, and determine something that might be happening to that person in the future. Material science is more from D-Wave. I'm going to really rush through this. This is developing different chemicals for organic LED displays, and they discovered that using a quantum computer they could actually model these sort of molecules. This is the holy grail where they want to get to, but over time they're really getting there fast. Some other papers, some cyber security applications, looking for friends and foe within a Syrian ISI type environments. And this is the Barcelona Supercomputer Center. This is a bit of a sort of like wind down, finishing off. This is not our headquarters. They stole our image there, but this is in the TV program. And this is very interesting. I'm just going to finish off here, Carlo, if you don't mind. These guys are now saying, okay, from the research that we've done, we believe that in 2019 we will be using the D-Wave machine to actually run some stuff that we've got going. So these guys here, and I encourage you to look at some of these YouTube things, they have, very similar to the Ocado grocery shops, they have this AGV system that allows robots to go around a plant and deliver parts. And it's a very small bound problem. They only have about 100 of these vehicles, and they believe that in 2019 they will actually put this into process, and it will save them 1% of their production costs. Similar sort of thing to Recruit. They're going to do a hotel booking system. Again, they believe they'll do this in 2019. And the biggest outrageous one, really, I think, is the fact that this is more VW slides, that there is a web summit. And at the 2018 web summit, Martin Hoffman, who is the CIO of VW, he said that next year when you come to this summit, we will have a quantum computing application on your mobile that you will be able to land at the airport, pick up this application, and order the most effective transport mechanism, whether it's a bus, a taxi, or a tram, to get to the web summit. That's going to be a lot of work, so we'll see how that goes. I'm going to stop there.
Thank you.
Perfect.
Thank you very much. Yes, you have to accommodate a lot of interesting presentation. Thanks you again. And the next speaker, I'm introducing Fabrizio Renzi from IBM, and speaking about IBM Q, quantum computers for research and business.
The speaker will be Federico Mattei shortly, but let me tell you something that I believe is important for you. I am here in Bologna. I'm the Director of Research, Innovation and Technology in IBM Italy. I lead the technical activity in this country, and I am pleased because on my birthday, the 24th of November, we opened the research center here in Bologna, where we are currently recruiting. That's the first point that we want to raise. And the second point I want to raise is that we are recruiting in the area of algorithm, creation of new algorithm around HPC, out of which also quantum will be a part. Therefore, if some of you is interested, at lunchtime I'll come back and we can open some discussion. I believe it's a good news regardless of IBM, not IBM, because in general it's a mission of my life to try to bring research in Italy wherever it comes. In the past we have mainly focused on the commercial side. It is important because of course we are a company like D-Wave, we are a commercial company, but we believe research is an area we want to do. And thanks to the Regione Emilia we did, and we'll do a cooperation with Cineca on this topic. Some of the people we are recruiting will be placed physically here in order to have a better cooperation with this. That's an initiative in Bologna, but the purpose is to expand here all over the country. With all the university here we are cooperating in a lot of ways, and we want to expand. We start here, but we want to expand as much as possible. In terms of physical location, this will be Bologna, therefore we look for people that live. What was the Julia Roberts movie? Live, pray, and no, eat, pray and love in Bologna. Eat is easy, pray you are called, love they say too. But okay, Bologna is the place where we are looking people at this stage. After we look for other places. Now the next stage is Federico Mattei. Federico Mattei is a PhD of our organization, PhD in physics. That now, thanks to quantum computing, will put him in his core strength. He is leading all the quantum activities for IBM Italy. Federico, you are called.
Okay.